everyone, thank you so much for joining the video. Today's learning objectives are to firstly look at the electrophilic attack on benzene rings, which results in substitution limited to monosubstitutions. And then we're going to look at nitration, which is an important step in synthesis, including the manufacture of explosives and formation of amines. And then we're going to look at Friedel-Crafts acylation reactions, which are also important steps in synthesis. So by the end, we should be able to outline the electrophilic substitution mechanisms of nitration and also acylation using an aluminium chloride catalyst. Now we're going to talk about electrophilic substitution. So the delocalized electrons of arenes, so of compounds with the benzene group, have a high electron density and will therefore attract electrophiles. So we get this reaction of electrophilic substitution. Remember that electrophiles are species with a vacancy for a pair of electrons to form a covalent bond. So the general mechanism that we have is that a bond forms between one of the carbon atoms of this arene and the electrophile. And the carbon must use electrons from the delocalized system of the arene, and so this delocalized system is temporarily destroyed. In order to get the stability back, the carbon loses a H+ ion, and the overall result is the substitution of the electrophile. So we substitute a hydrogen for the electrophile. So key things to note are that the delocalized system gets temporarily destroyed, and the carbon loses a H+ ion, and that's what's substituted out. So if we're going to look at a general mechanism of this, for example, I'm going to use benzene. So this is the structure of benzene, and then I'm going to add an electrophile. So electrophiles will normally be positively charged because they've got that vacancy for a pair of electrons. And then what happens is that because we've got a high electron density in the middle of this benzene due to the delocalization of electrons, they are attracted to this electrophile. And so a bond forms between one of the carbons of benzene and the electrophile. So what we get is, again, we draw the hexagon, but this time we're going to have a temporarily destroyed benzene. So the delocalized system is temporarily destroyed. And so on this carbon, we're going to have a hydrogen, and I'm going to attach the electrophile also onto this carbon. And one thing to note is with the first diagram of benzene that I've drawn, obviously we assume that each carbon has one hydrogen attached. So now we're just honing in on one of these carbons that I've attached the electrophile to. And one rule that we need to know is that when we draw a line, a dotted line here, how we've drawn this temporarily destroyed delocalized system, the two ends here and here can't exceed this green line. And so, for example, we could have a hexagon that looked like this. And if you wanted to add the electrophile, say, onto this carbon here, so you draw the hydrogen, and if you wanted to add the electrophile here, we then would draw a green line here, and the C that you're kind of drawing can't exceed this green line. So what we would draw would be something like this, and we'd have the positive. So looking back at our original equation, what happens next is that in order for us to get the stability of the delocalized system back, so to fix the delocalized system, this carbon, which has now attached itself to an electrophile, needs to lose a H+, so it needs to lose the hydrogen that it's attached to. And so what happens is that the electrons from this covalent bond move to this positive charge, and then we get benzene, and then we get benzene, but now with an electrophile attached, and the H+ comes out. Now we're going to look at nitration. So this is a reaction when one of the hydrogens in the benzene ring is substituted by an NO2 group, so nitrogen dioxide. And so we call it an electrophilic substitution reaction. And that's because the attacking group we have is the NO2, and the NO2 acts as an electrophile, and we're substituting one of the hydrogens, so it's a substitution reaction. So the reagents we need are concentrated nitric acid and concentrated sulfuric acid, and the sulfuric acid acts as a catalyst. The condition which we need is 55 degrees Celsius, and this is really important because this prevents further substitution. The electrophile that we're using is this NO2 plus ion, which is also called the nitronium ion. So as an example, we're going to look at the mechanism of the nitration of benzene. So the thing to remember about nitration is that first we need to actually produce the electrophile from concentrated nitric acid and sulfuric acid. So I'm first going to look at the equations for producing the electrophile. This will always be the first step of your mechanism. And so what happens is we have some nitric acid and also some sulfuric acid, and they react together to form H2NO3 plus and HSO4 minus. So why this happens is that the sulfuric acid is a stronger Bronsted-Lowry acid and so that means that it donates a proton or a H plus to the HNO3. So what happens is that H2SO4 is acting as the acid and HNO3 is acting as a Bronsted-Lowry base, so it's accepting a proton. And then what happens in the second step, so this is the first step we have, and then in the second step we have that this H2NO3 plus ion will go on to form this NO2 plus that we're after. This is the electrophile that we're going to use for the substitution reaction, and water. So this is the second step. And what happens here is that H2NO3 plus loses water. And so now we can write an overall equation for the production of the electrophile. So overall, we have that nitric acid added with sulfuric acid. So remember, they both have to be concentrated. They produce HSO4 minus and NO2 plus and water. So again, this NO2 plus is what we call the nitronium ion. And this is what's going to act as the electrophile in the reaction. So now we get on to the actual substitution. So what we have is step 2, the electrophilic substitution. So we first draw out a benzene. So we'll have benzene here. And then what we have is the electrophile, which is the NO2 plus. NO2, and I'm going to draw a plus onto the nitrogen. And now if you remember, what happens is that because we have these delocalized electrons in the benzene, this is an area of high electron density, and so it attracts the electrophile. And so delocalized electrons move towards this positive charge of the electrophile, of the nitrogen, on this nitronium ion. And so now what happens is that we've temporarily broken the delocalized structure. So we still have the outside hexagon of carbon atoms, but now we're going to have this broken delocalized structure inside. So I'm now going to hone in onto this carbon, which I'm attaching this electrophile to, and I've got the hydrogen. And remember that in order for us to fix the delocalized structure, we need to lose a H+. Well, the carbon needs to lose a H+. And so the electrons from this bond move towards the positive charge. And so what we form is we have benzene, but now attached to an NO2. And so this is nitrobenzene. And we also form the H+. And again, this is an electrophilic substitution reaction. So overall, as a balanced equation, including the production of the electrophile and this substitution, what we get is that we have a benzene added with some nitric acid, and we're going to use a sulfuric acid catalyst, concentrated, and the nitric acid is also concentrated, and we also use a temperature of 55 degrees Celsius to prevent further substitution. And what we produce is this nitrobenzene and also water. So again, we need to remember that this is an electrophilic substitution reaction, as the attacking group is an electrophile, it's the NO2, and we're substituting, this NO2 is substituting a hydrogen, and so it's a substitution reaction. And nitration is quite important because it's the first step in the production of explosives, and it's also important in the first step in making amines, which are used to make industrial dyes. Now I'm going to talk about Friedel-Crafts Acylation. So this reaction was discovered by Charles Friedel and James Crafts, and this type of acylation is just like any other acylation reaction. So what we mean is that it introduces an acyl group into another molecule. And as a reminder, the acyl group is just this R-C double bond O group. And when we react arenes, so compounds with the benzene ring, with acyl chlorides or acid anhydrides with an aluminium chloride catalyst, we form aromatic ketones, and this is via an electrophilic substitution reaction. This is actually a really important note because acylation that we've looked at before has been nucleophilic addition elimination reactions. However, this is also called acylation, but this time we're using an electrophilic substitution reaction. So please make sure to not get them mixed up. And because we're using this aluminium chloride as a catalyst, this means that we regenerate it at the end, because we know that catalysts aren't used up within the reaction. And so the reagent we use is either an acyl chloride with aluminium chloride catalyst or an acid anhydride with an aluminium chloride catalyst. And the condition is that we don't have any water to prevent the reaction of AlCl3. And the electrophile we're using is this general acyl group, so this RCO plus ion. And so first let's look at acyl chlorides. So we're going to look at the general mechanism for the reaction with benzene. So first we need to generate the electrophile. So this is the first step. And what we do is we have this acyl chloride, and this reacts with the catalyst, aluminium chloride. And what this forms is the electrophile and also AlCl4 minus. So we get R-C double bond O, and now there's a positive charge on the carbon because we've lost the chlorine. And the chlorine has gone on to the AlCl3, sorry. And this AlCl4 is actually a tetrahedral shape, and it'll look a bit like this. So we have aluminium and then Cl, 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 and then here we have another chlorine, and this will be a negative ion. And that's because this one of these bonds here, let's say this one, is actually a dative covalent bond because both electrons are from the chlorine. And so we have this tetrahedral shape. Because a dative covalent bond is still, it classes as a bonding pair of electrons. And so we have equal amounts of repulsion from all of the electron pairs. And so the bond angle, therefore, is 109.5 degrees, which makes the shape tetrahedral. So after we generate the electrophile, we then do the substitution reaction. So now we're substituting. So we start off with benzene. And then we have the electrophile. So we have this R, C double bond O, and a positive charge on the carbon. And then again, we have this area of high electron density where the denucleized electrons are inside the benzene. And so electrons move towards this positive charge on the carbon. And then what we form is we still have the hexagonal ring, but now we have broken the delocalized part of it. And we hone in on this carbon, so we've got bonded also to, and now it's bonded also to, carbon, double bond O, and an R group. And now what happens is that two of these electrons from this covalent bond then move towards the positive charge, so we lose the hydrogen. And so what we form is benzene, but now attached to this C double bond O R and also a H plus. So what we formed is actually an aromatic ketone, because ketones have the formula R C double bond O and then R dash, which can be equal to R or different. And so we have a benzene on this ketone and also an R group. So it's an aromatic ketone. So what we would get for the name of this molecule would be 1-phenyl, which means it's got a benzene ring on it on the first carbon, and then something -one, so propanone or butanone, depending on what R is. And then after this step, we then get a third step because we need to regenerate the catalyst. And so step 3 is regenerating the catalyst. And so what we do is we have the AlCl4- ion that we produced when generating the electrophile. And this reacts with the H plus that we've produced from the substitution reaction. And this forms AlCl3. So the AlCl4- loses a chlorine. And then this chlorine then reacts with the H plus to form HCl. And so now we've regenerated this AlCl3 catalyst from reacting AlCl4- with H plus. And now we're going to look at the reaction with acid anhydrides. So it's a very similar thing, but this time using an acid anhydride instead of an acyl chloride. So again, the first thing we need to do is the generating electrophile step. So a really important thing to note is that this mechanism is exactly the same as the one for nitration because they're both electrophilic substitution reactions. And so for this one, we have the acid anhydride that looks slightly different. So we have R and a carbon, double bond O, another O, and then a carbon, double bond O, and R. And then we add this again with the catalyst AlCl3, and then we form the electrophile that we're after. So this R, C double bond O, which is positive, and now we have another negative ion. So what we've done is we've split it up. So this bit has become the electrophile, so the positive bit, and then we have an ion formed from the rest of the molecule. So we have AlCl3, which is now bonded to this RC double bond OO, but it's a dative covalent bond again, and so we get something that looks like this. So this is a negative ion, and the two electrons have both come from this aluminium and are being donated to this oxygen, and so that's why we get a dative covalent bond here. And then again, the second part of the reaction is the substitution. So we have number 2, substitution. So we have benzene, and then we have the electrophile. So again, this RC double bond O with a positive charge on the carbon, and then again the electrons in the delocalized bit of the benzene are attracted to this positive charge on the carbon, and so they move towards this positive charge. And so they move across over to here, and then that means that we've broken, well, temporarily broken the delocalized section. So again, we draw kind of like a half C, and then we have the hydrogen, and it's now attached also to this acyl group. And then in order to regain the stability, we then lose this H plus by these electrons moving towards this positive charge. And so again, what we form is we have benzene with this C double bond O R and then the H plus ion. And so again, we have this one phenyl molecule. And we always have to remember that the catalyst is regenerated, so that's always the final step. So this time we're adding what would have been the AlCl4 minus for the acyl chloride, but this time we get this other ion, this Cl3Al, datively bonded to this C double bond OOR, and this reacts with the H plus, which has just been formed. And so what we get is AlCl3, which is the catalyst, and also a carboxylic acid. And so this is the catalyst. So when questions ask you to prove why AlCl3 is a catalyst, it's because it's used in the beginning to generate the electrophile and also regenerated at the end. So a really important thing to remember is that these are electrophilic substitution reactions because the attacking group is an electrophile, and we are substituting a hydrogen for this acyl group, this RC double bond O, and so it's an electrophilic substitution reaction.